Okay, so Josiah is adventurous, and well, yeah, he's using a Prezi, so hang on. You have the floor as soon as the presentation appears. There we go.
Good morning. My name is Josiah Hagan. I'm a researcher at Tipping Point, mostly using math statistical analysis to look at large volumes of network data. For the past couple of years, I've been looking at DGA traffic. Thanks to Daniel earlier with the DGA archive talk, and the Alexanders yesterday with the other DGA talk for giving an introduction to my talk, so I won't have to go too much in depth on the history of DGA or what they're used for. And in particular, I'm looking at classifying domains one at a time to determine whether they're DGAs or not. I've been doing this work for the last year with colleagues at HP Labs, including Miranda and Prasad. We wanted to move from something that was pretty primitive in what we had to collect DGAs to something with a little more teeth. So what are we trying to do? We want to classify domains first as to whether they're malicious or benign. We don't want to have false positive classifications of malicious domains because it's more expensive for us to say that something is malicious when it's actually just cheese. And then we want to take these classifications and drill down. And if we can, we want to say, OK, where did this come from? What family of malware? Or what type of benign domain is this? For the purposes of this work, what's not in scope is determining infected hosts. We sort of use this work as an input for other classifiers. We're only going to consider domains one at a time, and sometimes we may be wrong. So when you get thousands of requests a day, and some of them are wrong and a lot of them are right, you tend to be able to make a good prediction. So what did we do? Well, our solution is like many machine learning framework solutions. We have a training phase and an evaluation phase. When we're evaluating domains, in the IPS world, we're operating in real time and in line. We want to do things as quickly as possible, so evaluation has to be fast. For training, first, we have to gather a bunch of data labeled by family. Then we're going to take that data and look at some of the syntactical features that we can directly group things by, so that we'll create groups according to some syntactical features which agree for everything in the group. Then we'll build classifiers using machine learning, typically linear classifiers like logistic regression, to determine if things are benign or malicious within a given group. And then we'll use that to drill down to give the family or origin of the DGA, or the domain in question. Now, when we do this, our feature space may be quite large, so when we build the classifiers, we may want to determine which features are particularly salient for this group as far as classification goes. So you can imagine when we're evaluating, we're looking at domains one at a time as people are making requests. And again, we'll determine the syntactic features very quickly, and then apply our classifiers. So the first part of that is coming up with syntactical rules that allow us to group these domains. And these are, we call them the coarse and the fine syntactical features. The first of the coarse ones is the top-level domain. Malware families are typically restricted to several TLDs, or in the case of config, there are 100 and some odd domains. But they are somewhat rigid for the malware family. Then we look also at the length of the second-level domain. That's the part that comes just before the public suffix or top-level domain. Again, this doesn't have much variance within a given family. We look at the length of the prefix, everything that comes before the second-level domain in the domain name. And then we also look at the number of levels total within the domain. You could imagine that extracting this information from a string is pretty quick. We call these, in our classification scheme, these form the leaves of our data. When we're looking at the fine syntactical features, we want to consider everything, all of the families within a leaf. What are their regular expressions? Because we'll take these and then compute the intersections of the regular expressions, so that we can then have all the possible subsets of combined regular expressions for families within that leaf. That gives us 2 to the n, possible subsets, but in practice, many of the malware families use the same alphabets. We end up with the same regular expressions, and there are only a handful in practice. And we call these subparts of our leaves lobes. I don't know why we called them these things, but it just stuck. So you might get a sort of overall view of this where we have all the domains in question at the top, and then first we're separating them by these coarse features, the top level domain, the length of the second level domain, the length of the prefix, and the number of levels. And then from there, we take all of the candidate families within that leaf, and we group our domains according to the intersection of regular expressions that are matched for that domain. So after we've done this syntactical grouping, then we're ready to create classifiers using machine learning. And when we're creating classifiers, we need to be able to turn our domain names into a point in feature space. So to do this, we have to quantify everything that we can about a string. Here we have a string that's, maybe a couple dozen characters long on average. How is it that we turn that into something as a point in n space? Now again, we already know that the coarse and fine elements of the syntax for these domains are the same for everything within the lobe, and we're creating our classifiers within the lobe. So there are 4 main types of features that we extract from a given domain name. The first are aggregates. They're counts of different character classes. For the second level domain, we consider counts of character classes like, are they hex characters, consonants, vowels? Do they come from another language? And then we also look at some aggregates of bigrams. Namely, are there repeated characters like AA or YY in the domain name? And then we also look for how many non-linguistic bigrams, how many character pairs are there in the domain name that don't occur in any Indo-European or Finno-Ugric languages. And then we also look for overall counts, all the valid punctuation that's in the domain name, including the top level, not the top level, the second level domain and the prefix. And we also look for the count of RFC 1034 violations, which specifies the proper syntax for a domain name. So these would be some of those rules. There are only 22 of these buckets, which isn't a whole lot, and these aggregates give us a good idea of some notion of the shape of this, this domain. Next, we'll look at n-grams. N-grams are simply character counts, character pairs, and character triples. Now, we want to reduce the set that we're considering somewhat, so we compress our character pairs and character triples to 40 just by taking the alphabetic characters, the digits, and dot, dash, and underscore, and then putting everything else into the 40th bucket. So this is good. These features are good because they do capture linguistic versus non-linguistic elements. You'd imagine that a benign domain is generally going to contain some linguistic elements. People want to associate a domain with something that they can speak or understand. And these features are useful in separating those domains from ones which aren't. It's also intended to catch bias in the DGA's pseudo-random number generator. If they have some predilection for landing on certain characters or character pairs, this sort of statistical analysis will catch that. It's the same sort of game that you play in trying to decode something cryptographically, where you're just looking at sort of the expected frequency of given characters or character pairs, and then seeing what it is that you'd match. So, there are 256 ASCII plus characters. If we reduce these to 40, there are 40 squared and 40 to the third buckets for these 2 and 3 grams. That can use a bit of space. And if you just assume memory is cheap and you don't care about space, it still presents a problem with overfitting in machine learning situations when you have a large number of features compared to your number of training examples. And again, we're building this classifiers per lobe, so we've already kind of filtered our data into smaller buckets. then we can get something that looks very good in training, performs very well in training, but then when it encounters new data, it's overfit to its training data and it doesn't classify very well. So we need to perform feature selection on these sort of large feature sets to reduce our overfitting. The next set of features that we consider are the characters by position. And we do this both forward and backward through the domain name, excluding the top-level domain. So you can imagine Boolean slots for whether a character occurs in a given position in a string, and maybe limit the length of the domain name to 256. This allows us to catch fixed substrings in the string. So if we had an A at the beginning of every domain of a given family, then that bucket's always going to be filled. Or likewise for the backward direction, if an A is always the last character, then that bucket will be filled. There are a number of malware families that do have fixed strings, relatively fixed at least, only several options, maybe several dozen. And these features are very good for catching these sorts of things. Again, there are a lot of buckets to fill, so we end up with a problem of space and overfitting. The last set of features that we consider when sort of turning a domain into some point in feature space are word-based features. I mentioned before that linguistic elements are somewhat useful in distinguishing benign and malicious domains. So we extract word-based features from both the second-level domain and from the prefix, that stuff that comes before the second-level domain. We look at the overall count of words in the domain for a given dictionary, for a given minimum length. I chose English and words greater than 3 in general for my testing. We look at the maximum count of non-overlapping words, so how many words could be strung together that don't overlap in the domain. The maximum percentage of the domain comprised of words, so if we select greedily to cover the most of the domain or the second level domain or the prefix as possible with words, what percentage is covered by words. And then the length of the longest word. And again, we do this for both the second level domain and the prefix. This is really good at classifying benign versus malicious domains. Most people who are registering benign domains want you to remember it associated with some word, whereas DGAs typically not so much. It does turn out that it is also good for finding word-based DGAs because they are relying specifically on concatenating words. For instance, they almost always have a 100% covered by 100% of the characters are covered by words. And they also tend to have a very restricted maximum count of overlapping words, and they're easy to characterize by these features. Disadvantages are this takes time. In a sort of real-time setting, it may not seem like a lot of time to calculate these on relatively small strings, but they're sort of order n squared for both the length of the second level domain and the length of the prefix, and that's more time than I want to spend doing something. And then again, this can lead to overfitting where we might prefer to call something a word-based DGA when it's not. In the example that we saw in the DGA archive talk, there were a large number of supplebox domains that were pre-registered, likely valid. And here we would just go ahead and classify them as supplebox DGA and get a false positive. So that covers feature space, which leads us to results. How well do we do in classification? So normally in machine learning, you want to measure your performance by doing some cross-fold validation where you hold some data elements out that you don't train with, and then you see how well it performs on those. And we usually grade by precision and recall. And precision is our, you can think of it as our false positive rate. How often do we predict something as a class that it's not? And then recall is our false negative rate. How well do we catch the things that we're intending to catch? So, we do fairly well. We're trying to, in our sort of overall goals, we're trying to maximize the precision for benign classifications. We don't want to say that something is malicious when it's not. Now, doing domains one at a time and trying to use this as an oracle to determine whether a host is infected or not, that number is still not high enough because you're going to request many domains per day, and even a small false positive rate is going to flag some things as DGAs which are not. Well, how well does this do at classifying different malware families? You can see that for some of these families, it does quite well. And those tend to have a distinctive syntax. Even domains that we didn't have a number of training examples for, like Expero, it has consonant vowel dash, consonant vowel pattern. So it's pretty easy to pick up by classification. There are some things that we didn't do well with, and it seems that that's largely a case of data imbalances where we have much more data in given lobes for one family than another, and we just end up preferring that family, regardless of how we weight our classifier. So this leads us to several conclusions. Syntactical rules have helped our classification immensely. We do a lot better with the pre-filtering into leaves and lobes of syntactical rules. Having unbalanced data, it hurts. That when we don't have enough training examples for a given family, that we typically won't classify it very well. And that the results look good on paper, but when we put it into practice in HP's corporate environment, we're looking at 2 billion domains a day or so. It doesn't do as well. In particular, it will flag valid domains as word-based DGAs. We have noticed that some features are particularly good at classifying DGAs. The aggregates that I mentioned in the beginning are few and powerful. Looking at the most frequent linguistic bigrams and the opposite, those bigrams and trigrams which don't appear in any language we know, is also a very useful set of features. And then finally, the word-based features give us a lot of power. Another thing, just through experimentation, not really in the scope of this paper or talk, but in order to get past the false positives for the word-based DGA predictions, if we were to hash the words rather than sort of pre-storing a dictionary that maps the words one-to-one in feature space, but just compress the words into some other parts of feature space, we can also reduce our false positives. Again, this isn't a standalone solution. This is just answering the problem of how it is that we could build as good a domain classifier, one domain at a time, as possible. And that we'd want to, well, we do, use this information as inputs for other classifiers that then help us identify infected hosts. That's all I got. How about y'all?
Thank you. Okay, we have time for one question or two very quick questions. One, two, three. Okay, thank you.